Hey there, welcome back to 2241. This is our examples 2 video, and we'll pick up where we left off with problem number 6. Here, we're being asked to find all second partial derivatives of this function now. All right, it's a polynomial, so we should not have too much trouble, but again, we do want to be careful. So let's find our first derivatives first. dz dx. All right, and we kind of know how to do this at this point. We've got 3x squared plus 2xy cubed, and then dz dy 3x squared y squared minus 4y. And this is the exact same function that we started problem 1 with. But now we want to take the second partial derivatives. So what does this look like? Well, we have a little bit of a different notation for them. So we have dz, or d2z dx squared. And this just means take another x derivative here. And that gives us 6x plus 2y cubed. But now we've also got dz dy dx. So this means do a y derivative after doing an x derivative. So I take the y derivative of this function right here. That now gives me 6xy squared. All right. Next up, I have the second partial derivative of z with respect to x after y. And that means take the derivative of this function with respect to x. All right, that second term is definitely going to go away, and we're left with 6xy squared. Oh, and look at that, these two things are equal. This is an application of Clairaut's theorem. So, by Clairaut. So these two functions are continuous. This function has continuous derivatives of all orders. So these mixed partials in different orders are equal. All right, last thing that we need is our second partial with respect to y. And this is going to give us 6x squared y minus 4. And that's it. There's a little bit of interesting structure that we can write out here for second partial derivatives. So we start with our function z, and then if we take an x derivative and a y derivative, so d dx, d dy, we get zx and zy. Okay, if we take another x derivative, we get zxx and zxy. It's kind of annoying, but the notation says that y comes after x here, whereas over here, y comes after x in the opposite direction. All right, and this was a y derivative. Same thing over here. X derivative gives us zyx, and y derivative gives us zyy. And so what Clairaut's theorem does is it squashes these two things together into one part of the tree. Squashes the tree together, and now you have two branches connecting. We can keep going here. We can do the x and y derivatives of these functions. But things start to get a little messy. So we have zxxx and zxxy. And then same thing for these, zxyx, zxyy, here, 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 and here. Same sort of thing is happening. Z, Y, X, X, Z, Y, X, Y, Z, Y, Y, X, and Z, Y, Y, Y. Okay, and so now what Clairaut's theorem is going to do is it's going to squish together anything that has the same number of x variables and y variables. So let's see, we have two x's here and one y, same here and same here. And then here we have two y's and one x, same here and same here. So Clairaut's theorem is going to stick all three of those together. There we go. All right, and then these guys also get stuck together in a different blob. And so now we've got this tree that's sort of like squishing a bunch of stuff together. And if we try to draw the reduced tree, let's do this down here. So we'll have z, zx, zy, and I'll just write zxy for my mixed partial. And then zxx, zyy, right? Zxxx is definitely different. Zyy is definitely different from the other ones. But now I have a bunch of derivatives that end up being the same. And that's because these guys all got grouped together. And so I can just write zxxy and zxyy. Now I have a sort of weirdly oriented grid of derivatives. All right, so that's just some interesting structure in partial derivatives that you don't get with single derivatives. Down here, let's go ahead and compute a fourth derivative. At this point, we've kind of got the idea. We're just applying derivative rules over and over again. So zx is cosine 3x plus yz times 3. So we'll put the 3 up front. Zxx is minus 9 sine of 3x plus yz. Zxxy, my next derivative I need is a dy, is now I take the y derivative and I get a z out of the chain rule. So we have minus 9z cosine of 3x plus yz. And now I take a, oh, that shouldn't have been a z, I'm sorry. That was supposed to be a w. So let's fix that real quick. W is what I should have been writing here. W, x, x, y, now z. Okay, here we go. We have to use the product rule. We have this function times this function. So derivative of minus 9z is just minus 9 times the cosine of 3x plus yz. And now plus this function times the derivative of this one. Well, this one is going to give me a negative, so I'm just going to leave the plus there and not write the minus 9. So we have 9, and what am I going to get out of my chain rule here? I'm going to get a y. So 9yz sine of 3x plus yz. All right, and there's our fourth partial derivative of w with respect to all of these things. Alternatively, we could have swapped the ordering of here. We could have done the derivatives of y and then x and then z and then x, or any other swapping of these things that you might want. You should end up getting the exact same answer at the end because all of these functions involved are continuous. So we have 3 times x plus y times z. All of that is continuous. And then we take the sine of everything. Sine is a continuous function, so we have very little to worry about here. Our next problem is a little more interesting. We want to show that a function given to us is a harmonic function, or remember this means solution to Laplace's equation. So let's write down what Laplace's equation is one more time. We've got uxx plus uyy equals 0. Okay. And while we're looking at this, what this means essentially is that if you look at the derivative in the x direction and in the y direction here, they should sort of be opposite to each other. And the second derivative measures essentially the concavity of a function, if you remember that from Calc 1. So what we should have is something that looks like maybe this in the x direction and this in the y direction. Make it a little more like that. There we go. So we should have sort of a hyperbolic paraboloid type shape at every point. And so that's why these functions are sort of interesting. They have that sort of thing happening everywhere. All right, so let's show that this does work, that if I take the second fixed partials, unmixed, of u and add them together, I get 0 out. That's how I check this. So I just need to compute u xx. All right, so I take two derivatives with respect to x. The sine of y has no x's in it, so I just take the derivative of e to the x. But that derivative is itself twice. And then same thing here, uyy. I take the derivative of sine y with respect to y twice. And I know that's just going to introduce a single minus sign, because I'll cycle to cosine and then I'll cycle back to minus sign. All right, and now I can see that if I add these up, I get 0. So I have exactly what I want, that this is a solution to Laplace's equation. All right, I think we have one more here, yep. And I might need a little bit more space, so let's move this up just to be safe, and check that another thing is a solution of another equation. So I rewrote the wave equation for you here this time. UTT equals c squared uxx, and this is our function u here. So if I now do the same thing I did a second ago, I just need the second x derivative and the second y derivative. In this case, let's compute the first derivative first, and then we'll compute another derivative. So here we have cosine of x minus ct times the derivative of x minus ct with respect to x. That's constant, so it's 0 in the derivative. That gives me a 1. So I just have cosine of x minus c times t. All right, now I take the derivative of that one more time with respect to x, and the same sort of thing happens. I have minus sine of x minus c t. All right. Now I need the second t derivative. I'll write this the same way. Again, I'm going to take the derivative of the sine function and get cosine, but now I take the derivative here, and I get minus c out. So minus c cosine of x minus ct. Let's do that one more time. And now I get c squared sine of x minus c times t. Oh, missing a minus sign here. Minus c squared there. Okay, and now, yes, this is exactly the relationship that I want. I can see that if I multiply uxx by c squared, I get exactly utt, or I can just notice that this right here is minus uxx. And so I have the equation utt equals minus c squared times minus uxx, or the wave equation.